The voltage V in a linear circuit is described by the differential equation dV dt plus 1.8 V equals 6.3 millivolts per second. We are going to use the method of Laplace transforms to find a general solution to the differential equation. Okay, so we put L in front of each term in the differential equation. L, as we know, is a linear operator, so we can pull out the 1.8 here for the second term. V is some function of time, so you can write that in if you like. Now, for L of V of t, we can write big V of s. We're going from the time to the s domain. Now, what about L of the derivative? Well, that's s times big V of s minus little v of 0. So little v is our function of time, where the time is 0. Now we need to get L of 6.3. If you go to your transform tables, you'll see that the Laplace transform of 1 is 1 over s. So the Laplace transform of 6.3 can be written Laplace of 6.3 times 1. Using linearity, that's 6.3 times the Laplace transform of 1, which is 6.3 times 1 over s, or 6.3 over s. Now little v of 0 is unknown. That's why we are getting the general solution to the differential equation. Okay, so we'll have to carry little v of 0 throughout this calculation. Okay, we need to isolate big V of s. So we factor out big V of s on the left hand side, bring minus little v of 0 over and divide across by s plus 1.8, and then you can multiply above and below by s to get this here. Now, instead of v of 0, I'm going to write c. After all, it's just a number, it's just some constant. It's the value of little v when t is 0. Now we'll have to get the inverse Laplace transform of this expression here. And notice that the denominator is a quadratic, but it's got an s term. So we are going to change the form of this denominator by completing the square. So we get half the coefficient of s. Half of 1.8 is 0.9. So we write s plus 0.9 here and square it. If we square this out, we'll get s squared plus 2 times 0.9 times s, which is 1.8s. So we do get this back. But then we get an extra term that we don't want. 0.9 squared is 0.81. So we need to subtract off this 0.81 to leave us with s squared plus 1.8s. Now notice that I've split this fraction into two fractions. I've taken 6.3 over the denominator and c times s over the denominator. Okay, if we go to a table of Laplace transforms, you see that we will be working with expressions of either this type here, where the denominator is s minus a constant squared minus a constant squared, or an expression of this type, where the denominator has the same form, s minus a constant squared minus a constant squared. So we need to get our expression into the form of either, well, actually both this fraction here and this fraction here, and then we can read off what the inverse transforms are. So the first fraction here has a constant on top, so I haven't changed anything here. We don't have to do too much adjusting to this fraction here. But look at the second fraction. The second fraction has s on top, and we want these quantities to look the same. So I've had to write s plus 0.9 times c on top here. Okay, so if we multiply this, we get sc plus 0.9c. Well, sc will just give us back this here, but the 0.9c gives us something that we don't want. So we need to compensate by subtracting off the 0.9c. So we have to subtract off this to get rid of it. Now we can put the first and last fraction together. That to give us a fraction with just a constant on top. Okay, the 0.9c is just a constant. Okay, so here we are. Now, this is the term with this is the fraction with the constant term on top, and here is the inverse transform that we are going to use, of course. So notice that we've b on top and we've b squared in the denominator. So we can see here that b squared is 0.81. So the square root of 0.81 is 0.9. So we need to have 0.9 on top. Okay, so I've written down the inverse transform of this first fraction here. Well, we will evaluate it soon, but I've gotten the first fraction into the required form. So we have to have 0.9 on top. That corresponds to our b. and to compensate for that we have to divide by 0.9, and I've taken out the numerator, which is just a constant, of course. Okay, now what about the second fraction? Well, the second fraction is let's see now. Well, it's in the required form actually, except for this c, which we can just pull out. Okay, we can see that a corresponds to minus 0.9 actually. S minus 0.9 is s plus 0.9. B squared is 0.81. Okay, so it's in the required form, so we can take out the c, so we want to get the inverse transform of s plus 0.9 divided by s plus 0.9 squared minus 0.81. So for the first inverse Laplace transform, we have to get e to the power of a times t, where a is this value here. A is 0.9. Well, actually a is minus 0.9. Okay, in the formula we have s minus a. So minus a is 0.9, or a is minus 0.9. Then we have sinh of b times t. Well, b squared is 0.81, so square root of 0.81 is 0.9. Okay, if we look at the second inverse Laplace transform and compare to the general form, we can see that a is minus 0.9. Minus a is 0.9, or a is minus 0.9, so we have e to the minus 0.9 t. Then we have cosh of b times t, where b is 0.9. Now, if you like, you can replace sinh of 0.9 t with its definition using the exponential function. Okay, you can just look this up. And of course you can do the same for cosh. Its definition using exponential functions looks exactly the same, except we have a plus sign here instead of a minus sign. Okay, next I've multiplied e to the minus 0.9 t into the numerator here to get this here 1 minus e to the minus 1.8 t, and I've done the same over here. E to the minus 0.9 t times the numerator of this fraction gives us 1 plus e to the minus 1.8 t. Next, this half is taken out. We have 63 over 9 here. That becomes 63 over 18, and then we have 0.9 over 9, or minus 1c becomes minus a half c. Next we can multiply everything out and simplify. Simplifying further, we get our solution. Little v of t is c minus 3.5 e to the minus 1.8 t plus 3.5, where c is the value of little v at t equals 0. Of course, we could have solved this equation much more easily by using a substitution method. We could have written it like this and replace this expression here with a single variable. You know, we could call it p or something, and we could work from there. We also see, of course, that this is a linear first order differential equation. We could use an integrating factor method to solve it. In part 2, we want to get a particular solution that satisfies the initial condition v of 0 equals 8.5. So this is replaced with 8.5. So this is our particular solution of the differential equation. Now let's look at the graph. Well, when t is 0, we have 5e to the 0 plus 3.5. That's 5 plus 3.5, which is 8.5. Well, we were already given that, of course. V at time 0 is 8.5, so the graph starts at 8.5. Now, because of the minus sign here, of course, we have a decaying exponential function. So v of t will decrease as time goes on. So what happens as t approaches infinity? Well, the exponential term e to the minus 1.8 t will approach 0. So we'll end up with 5 times 0 plus 3.5, or just 3.5. So the graph is going to decay towards asymptotically towards the value 3.5.